Okay, so I will have here this voltage is equal to, this is the leakage coefficient times the speed times the stator inductance times the stator current on the axis. This is my first term. Okay, this is the decoupled control of the active and reactive power. And the other one, and the other term is equal to the leakage coefficient times the speed times the stator inductance times the stator current on Q axis. So it means I am decoupling the control of the active and reactive power. So this is the decoupled items of the stator voltage, right? This is the decoupled items of the stator voltage. Okay, so pay attention to the block diagram. I will have a dual closed loop controller structure. Okay, I will have a dual closed loop controller structure. So I will have the outer control is the rotor flux. Okay, and the electromagnetic torque. This is the outer control. And besides, I will have a current inner loop. Okay, I will have here a current inner loop. So I will have two loops. Okay, this is a dual closed loop controller structure. Okay, so pay attention to this part. The current inner loop is adjusted through the proportional integral controller plus the decoupled compensation items. Okay, plus the decoupled compensation items. In this way, I am adjusting the current inner loop. Okay. So once again, in order to adjust the current inner loop, I will use the PI controller plus the decoupled compensation items. The PI controller plus the decoupled compensation item. So according to the rotor flux vector orientation, we know the rotor flux on D axis is only related to the D axis. It means to the stator current on D axis. And in case of the constant rotor flux, okay, the electromagnetic torque is only related to the Q axis. In other words, I will have here the stator current on Q axis. Okay, therefore, the main conclusion here for the decoupled control of the active and reactive power, I am saying the rotor flux on the axis and the active power, this is for the first decoupled term, and the electromagnetic torque and the reactive power, okay, are decoupled with these two decoupled items from the stator equation box. Okay, this is the block diagram of the generator side inverter control. So once again, the flux and active power of the generator can be controlled by alternating the D and Q axis component. This for the flux and active power, and the stator current on quadrature axis for the electromagnetic torque and the reactive power. So I will have the decoupled control on the flux and electromagnetic torque. In other words, the decoupled control of the active and reactive power. We have already demonstrated with these two the decoupled items of the stator volts. Okay. Okay. So on the other hand, this is for the, we have already finished for the squirrel cage induction generator. That is it for the squirrel cage induction generator. So let's continue with this. Let's continue with the permanent magnet synchronous generator. Okay. So let's continue with the permanent magnet synchronous generator. Once again, this is the control system of the generator side converter. But in this case, I am working with a permanent magnet synchronous generator. Okay, so once again, for the generator side converter, I will have three different control strategies. Okay, and the first one is the maximum torque control. This is the maximum torque control. Okay, is this one. What happened in this type of control? Once again, I am working with a rotor reference frame. Okay, this is the DQ reference frame with this capital letter, okay? For the rotor reference frame, the electromagnetic torque equation, okay, is equal to, so we have already demonstrated this equation in the previous lecture, is equal to 3/2 times the number of poles. Taking the imaginary part, this is one way in order to compute the electromagnetic torque. I will have here the stator voltage, this is conjugate, okay, times the stator current. Okay, this is my first way in order to compute electromagnetic torque with the stator flux and the stator current. Another way is using the DQ components. Okay, so we have already demonstrated this equation too. So the electromagnetic torque is equal to 3/2 times the number of poles. Okay, I will split up in two components. Okay, so I will have here the stator flux on the axis. Okay, times the stator current on Q axis minus I will have here the stator flux on Q axis plus the stator current on the axis. This is the second way in order to compute electromagnetic torque. But we have the last equation in order to compute electromagnetic force as a function of the direct axis inductance and the quadrature axis inductance. Okay, my final equation is, in order to compute the electromagnetic torque, is equal to 3/2 times the number of poles. Okay, I will have here the direct axis inductance. Okay, minus I will have here the quadrature axis inductance times the stator current on D axis times the stator current on Q axis plus the magnetizing flux. No, this is the permanent magnet flux. Okay, times the stator current on the axis. Okay, so do you remember we assume the direct axis inductance is equal to the quadrature axis inductance. Okay, this is an approximation. Okay, so therefore I will say the electromagnetic torque, okay, is equal to 3/2. I will have here the number of poles times, this is the permanent magnetic flux, times the stator current on Q axis. Okay, so what happened in this case? The electromagnetic torque only depends on the stator current on Q axis. So it's possible to carry out the control. It's possible to carry out the control of the electromagnetic torque only with the stator current on Q axis. This is my first mode of operation. Okay. In other way, this is the control strategy. My first control strategy. Okay, the maximum torque. Okay, the second one is operating with unit power factor. Okay, the unit power factor. For this case, the stator current on the axis is controlled to adjust the reactive power of the machine. Okay, the reactive power of the machine required for the generator. Okay, so pay attention to this part. The reactive power of the machine is not necessarily related to the reactive power exchange with the grid, between the wind turbine and the grid. This is a different reactive power. This is the reactive power for the machine. And this is the reactive power for the grid. In other words, is the reactive power is exchange between the wind turbine and the power grid. Okay. For this case, that is the reason. Do you remember? For this, in order to control the reactive power of the grid, I will use the quadrature, the stator current on Q axis. But in this case, because I am working only with the machine reactive power, I am adjusting only the stator current on the axis. It's different, right? Is different. So in this way, I will get the unit power factor. Okay, in this case, the reactive power is equal to 0, but I have a problem. The rate capacity of the converter is reduced. In the previous case, the reactive power we know is different to 0, but the rate capacity of the converter is increased. Okay, so in this case, I will have this problem. The rate capacity of the converter is reduced. Okay, this is for the unit power factor. Okay, this is for the unit power factor. Okay, and the last one is a constant stator voltage. Okay, and the last one is the constant stator voltage. So for this case, in the constant stator voltage, once again, I will have here the reactive power is different to 0. Okay, and finally, it's possible to say the stator active power is equal to 3/2. I will have here times the stator voltage on the axis times the stator current on the axis. This is for the active power. What about the reactive power? The reactive power is 3/2 times the stator voltage on the axis times the stator current on Q axis. So I will have 3 control strategies. Okay, the first one is the maximum torque. In this case, the reactive power is different to 0 and the rate capacity of the converter is increased. Okay, for the second control strategy, I will have here the reactive power is equal to 0. That is the reason I will have a unit power factor. Okay, but I have a problem. The rate capacity of the converter is reduced. Yeah, for the last control strategy, I will have a constant stator voltage. For this case, the reactive power is different to 0, and therefore I am capable to compute the stator active power and reactive power. So now let's continue with the control system of the generator. In this case, is the permanent magnet synchronous generator. So from the previous equation, we know the stator voltage on the axis, we have already demonstrated this equation, is equal to the stator resistance times the stator current on the axis, plus I will take the derivative of the direct flux minus the electrical speed times the quadratic flux. And this is equal to the stator voltage. Okay? The stator voltage on Q axis is equal to the stator resistance times the stator current on Q axis plus I will take the derivative with respect to the time. This is the quadrature flux plus the electrical speed times the direct axis flux, and this is equal to 0. I am working with a permanent magnet synchronous generator. What about the fluxes? In order to have the dynamical model, okay, I will say the stator flux on the axis, okay, is equal to, I will have here the stator current on the axis plus the magnetizing flux, the permanent magnet flux, and this is equal to 0. Okay, and the stator flux on Q axis is equal to the inductance, okay, times the stator current on Q axis, and this is equal to the negative. I will have here the stator voltage over the stator speed, okay, over the stator speed. So substituting the direct axis voltage is equal to the inductance times the stator current on the axis, and the quadrature axis is equal to the inductance times the stator current on Q axis. Okay, so substituting here, okay, I will get the following equations. So I will say the stator voltage on the axis is equal to the stator resistance times the stator current on the axis plus the inductance. I will have here the derivative of the stator current on the axis with respect to the time minus I will have here the electrical speed times the inductance times the stator current on Q axis. Okay, and the stator voltage on Q axis is equal to the stator resistance times the stator current on Q axis plus the inductance. I will take the derivative. This is the stator current on Q axis. Okay, plus I will have here the electrical speed times the inductance times the stator current on the axis plus the permanent magnet flux. Okay, so with this equation, the active and reactive current are completely decoupled in the stator voltage reference frame. Okay, and the corresponding control voltage vector are coupled. Okay, so finally, the main conclusion is the stator for this topology, permanent magnet synchronous generator, for this generator is equal to 3/2, is similar, right? Is similar to the previous equation, the stator voltage times the stator current on the axis. And the reactive power is equal to negative 3/2 the stator voltage times the stator current on Q axis. So this is the dynamical model of the permanent magnet synchronous generator. Okay.